Hello students, good morning. So today we will be studying regarding strain energy. It is a part of module 5. So let us try to define what is strain energy and understand what exactly is strain energy, how it comes into picture. At first let me start with the definition. So strain energy is defined as the internal energy which is stored in a material, which is stored in a material which is loaded within its elastic limit. So first let me write down the definition of strain energy. It is the internal energy. It is the internal energy which is stored in any material which is loaded within its elastic limit within its elastic limit. SI unit is Newton meter. Right? So this is the definition of strain energy. For example, what I can say is strain energy is found in springs. So this you can take as an example. Strain energy is found in springs. Now what you observe in springs, you observe that whenever a spring is loaded, let us say it is tensile loaded, okay, you are going to pull it from either side, its length is going to increase, right? When you are going to pull it from either side, its length will increase, and whatever pull you have applied, so that is creating a stress. So when there is stress, there will also be a strain. So whatever is the strain available in the body, or whatever is the load which you have applied, so that is available in the body as a strain energy. Now that is the reason I am calling it as internal energy. It will be available internally into the spring. Why? Because the moment I release this load from the spring, what happens to the spring? The spring goes back to its original position. Why it is going back to its original position? Reason is simple, because it is having some internal energy, right? उसके अंदर वो energy था, that is the reason it has gone back to the original size. If that energy was not there, then it could not have gone to that original shape and size, right? So once again I'll tell you, you take a spring, you just apply certain pull, then the energy stored inside the spring at this instant, I call it as strain energy. The moment I release this, it goes back to its original shape. Why? Because of the presence of internal energy, right? Now this was the example of a spring. Like this you can take any material, but the important condition here is the loading should be within the elastic limit. Loading should be within the elastic limit. अगर आप उससे भी ज़्यादा load करोगे, then the material goes into the plastic stage and the deformation will not be entirely recovered, right? So that is the definition of strain energy. Best example is example of springs. You can also take a rubber band, normal rubber band, which you'll be using in day-to-day life. So you just pull it, it will be extending, strain energy will be stored into the band, and the moment you release it, it goes back to its original shape and size, and that is because of the presence of the internal energy. And very important point to be noted here is this scenario is applicable only when you load the material within its elastic limit, right? If it is more than that, then sorry, it is not possible, because it will be only partially regaining its shape, right? Then other things come into picture, that is residual stress and all those things. So as of this particular topic, those things are not relevant to us, so I'm not discussing that. So that is the definition of strain energy. Example could be strain energy found in springs, at any other material which is loaded within elastic limit. Now sometimes it is also known as sometimes It is also known as work performed work performed during elastic deformation. Elastic deformation. Now what does it mean? Now I'll take the same example of spring or the same example of rubber band, right? Work performed. What is work performed? Force into displacement. I told you I will be pulling the spring from either sides. So जितना भी displacement हो रहा है multiplied by whatever force I have applied, that gives me work. So work performed during elastic deformation. So that is also called as strain energy, because let us say the deformation right now is 2 mm and the force applied is say around 10 newton. So 10 into 2 is 20 newton meter, right? So that 20 newton meter is nothing but the internal energy which will be stored. So जितना आपने वर्क किया है मटेरियल के ऊपर विद इन द इलास्टिक डिफॉर्मेशन लिमिट, सो उतना ही स्ट्रेन एनर्जी उसके अंदर स्टोर होगा. क्लियर? It's as good as, I'll give you a parallel example so that you can remember things easily. Suppose you are filling petrol into the tank, and let us say that it is such an environment over there that the petrol will not evaporate, right? So what I'll do, I'll just take the petrol and I'll just pour it into the fuel tank. Let us say I have poured 1 liter of petrol, and if you check into the fuel tank there will be 1 liter of petrol, right? Ideal condition is vaporization or evaporation is not happening, right? So same thing is happening here. So work performed during elastic deformation is nothing but whatever petrol you are filling, and strain energy is nothing but whatever is the petrol within the tank, right? So that is an analogous example, just so that you can correlate and understand this statement. So sometimes it is also known as work performed during elastic deformation. Next important thing is strain energy. Strain energy depends on the applied load. Strain energy depends on the applied load. And what does this mean? It means that the load may be so there are three types of loading what is generally observed. First one is gradual load. So load is applied in steps. Step by step you are going to apply the load. Next is sudden load. So as the name itself suggests, entire load is applied at a single stretch. Suppose if you are applying 20 kilonewton load, here in gradual load what happens? 5 kilonewton, 5 kilonewton, 5 kilonewton and 5 kilonewton. You are applying it 4 times step by step. But in sudden loading, entire 20 kilonewton load you are going to applying at a single instant. And at last you are having third one, which I call it as impact load. Impact load. What is this impact load? I'll just write here in bracket. It is nothing but load falling from a height, right? So from certain height, if a load is falling, then it creates an impact load. Now the expression for strain energy is given by the expression for strain energy is given by, okay, so it is strain energy is equal to U. I told you it is nothing but internal energy, so it is U. So that is equal to sigma square divided by 2E into volume. Right, so this is a general expression for strain energy. U is equal to sigma square divided by 2E into volume. Right. Now I'll show you how I got this. अभी तो मैंने इतना ही कह दिया कि this is an expression for strain energy. I have not yet derived that. Now I'll be going through the derivation and I'll be showing you how exactly I got this. Right, so let us start with a small derivation, not a big one. Hardly it will take around 5 minutes to solve that. So strain energy in axial loaded member. So let me write the title as strain energy in a axially loaded member. Right, so in order to calculate this, what I'll do, I'll just take an example of a prismatic bar. Right, let us say it is having some axial load on the center axis. Okay, और जो axial load का magnitude है, it is F. Right, now in order to derive this, what I can say here is, let us consider a prismatic bar. You write all those things. Let us consider a prismatic bar of length L. Let me say of length L, and it is subjected to a force F. Right, now in that case, just right here, stress is equal to, stress sigma is equal to F divided by A, where A is cross sectional area. Clear? So this is a known thing. Now this stress or this pull will create a strain energy. This stress bar pull will create a strain energy that is stored in the member. Right, now how I arrive to this particular expression, I'll show you. Okay, now we were dealing with strain energy in a axially loaded member. So now I'm just drawing a graph. So this graph will be for load. F is the load applied on the member, and here let us say it is deflection. It is deflection. So deflection is dl. Right, now what you observe, you have taken an axially loaded member and you are applying certain force F. What happens to the deflection? As and when you apply, as and when you go on applying the force, the deflection goes on increasing. The deflection goes on increasing. So what I want to tell here is, it will be like this. It will be a linear straight line. Right, so जैसे जैसे आपका force का value बढ़ेगा, very similarly the deflection will also increase. Right, now in this, what I'll do, if I just drop a perpendicular here like this. Right, now here this energy which is stored, or the area under this curve, now this is nothing but energy stored or strain energy stored. Right, so this is nothing but, let me use a different colored ink. I'll just write here strain energy stored. Right, so the area under the load reflection curve, gives me strain energy stored. So therefore, right here, strain energy stored in the member will be equal to area under the load deflection curve. Right? So how is that denoted? So that is given by 1 by 2. This is triangle, right? Half base into height. So 1 by 2. Now deflection is dl because this base is dl into height. So height in this case is f. Right? Now I'll take this as u because this is strain energy stored and we know that it is denoted by u. So therefore u is equal to 1 by 2. Now I'll make some substitutions here. What are those substitutions? I'll just write it here on this side. So very important substitutions, so please don't neglect this. So we know that deformation of an axial member, that is dl, is elongation, or you can call it as deflection or deformation of axial member, is given by FL upon AE. FL upon AE. Right? Now I'll be asking you one question. What is this F by A? क्या हो सकता है? It is nothing but load divided by area, so it is stress. So therefore dl is equal to F by A sigma into L divided by E. Right? Now also, so that was one term. Now we know that sigma is equal to F divided by A. So this implies F is equal to sigma into A. Right? I hope you agree with these two expressions. I am writing it at the side because these are not directly related to my derivation. I'll be substituting here and you should know how I got that. Right? So what is dl? dl is sigma L by E. Sigma L by E. And what is F? F is sigma into A. So now you can just check out U is equal to 1 by 2. So it is sigma into sigma is sigma square divided by E. So this is L into A or A into L. So therefore U is equal to 1 by 2 sigma square. You can take here E 1 by 2 into sigma square. What is A into L? Area into length. It is nothing but volume. It's nothing but volume. I can just make a note here. So this area into length gives you volume. Right? So that is how you got this expression for strain energy. Okay. Next, after you understood this expression, next point will be resilience. So what is resilience or definition of resilience? So the property of a material by virtue of which it absorbs energy when loaded and gives back the same energy when unloaded in order to regain its original dimensions. Original dimensions is called resilience. Is called resilience. Right now, that's it. That is the property of a material by virtue of which it absorbs energy when loaded. जब भी आप लोड करोगे एनर्जी स्टोर करेगा. जैसे ही आप external load हटा दोगे तो it will be regaining its original shape. So this property of all the materials, any XYZ material you take up, right? So that property we call it as resilience. Next point is modulus of resilience. Modulus of resilience. Now it is nothing but strain energy stored per unit volume. It is the strain energy stored per unit volume. Now here this is important. So modulus of resilience. So what is strain energy? Strain energy is sigma square divided by 2e into volume. Right? So this expression divided by per unit volume. So therefore modulus of resilience is equal to sigma square divided by 2e. Right? Now the last important topic for today's session will be stresses due to the types of load. Okay, so the last topic for today's class will be expression for stresses depending upon the type of loading. So I told you there are three types of load. So for the first case, it is for gradually applied load. Gradually applied load. So expression for stress sigma will be equal to the normal one, that is P by A, or you can call it as F by A, whatever you may take it, P or F. Right? So unit will be in Newton per meter square. I am writing the SI unit. Now for suddenly applied loads, sigma will be equal to 2F by A. And third one is for impact loading. Impact loading. Now here for impact loading, the expression for stress will be sigma is equal to F by A plus under root of F by A the whole square plus 2 times E divided by A into L. Okay, here you can just check out sigma is equal to F by A plus under root of F by A the whole square plus 2EF H divided by A into L. Now impact loading, I have just shown you an example. So there is say a certain rod and it is having a collar, so that whatever is the mass falling or load falling, it should not come out. Okay, so this is the stop point, or you can call it as a device which is going to stop the moving load under the action of gravity. Now when this load is left from certain height, it will come and it will impact on this collar. So this is the height H, right? Young's modulus E is known. H will be given to us in the problem. Cross sectional area will be known. So whenever this will be coming from this point and it will come and hit this collar, so in this case whatever is the load generated or this kind of stress, we call it as impact stress, and this kind of loading we call it as impact loading. So in impact loading, this is the expression for stress. Right, so that's it for today's session. In the next upcoming sessions, we'll be having some derivations, and thereafter we'll be following with the numericals. That's it for today's session. Have a great time. Bye bye.